Okay, so let me catch up what we talked about last time and then continue from there. All right. So we stopped talking about uh, another way to solve the problems on this little change thing, which is a dv by dt, right? So whenever we have a dv, the population growth over time. So this is a small change on the population growth due to the small change in time, right? So that's what we talk about. And I introduce a few things to solve this. We talk about something called irrational numbers. The Euler number is one of them. The Euler is nothing but the value we can get close to 718 to something like that. So this is the number, right? And then I was introducing you something called log, right? Base 10. If I have log base, so let's say 1000 here. So that is equal to 3, we said, right? So how are we going to measure this? The best way to remember it is the beak of a bird, or we call it Tarzan. So which is the base here and the power here. So this means 10 to the power 3 is equal to 1000. This is what it is. So when you're writing it in a log manner, this is how you write it, okay? And so this is base, which is a 10 right here, okay? So it's just like the Tarzan hang on a string and just swing like this. So this is the order of it, right? So this is the order of it. Or I just say beak of a bird is the same thing, right? Okay. So that is best way to remember logs, right? The order of the log. And if you have, for example, log base 10, 10,000 here, that is equal to 4, right? So that is 10 to the power 4 is 10,000. So that's what it means. And then there's another one, which is log to the base e. We call this ln. So if you ever seen something ln, this is what it means. So instead of a 10 base, we're talking about e base, okay? And so that's what we are talking here. So we're using both that concept in order to calculate this one, which is a dp by dt, right? Why? Well, these are more important properties. We can say that e to the power ln x is equal nothing but x value. And if it is x, then x is greater than 0, obviously. And then ln e to the power x is equal also L. So these are two things, that properties that is very important when it comes to the logarithm. Don't worry about it. If you don't understand it, just keep it in mind. Those are two factors that we're going to use. Right. All right. All right. So then I ask you to remember this slide right here. It's very important, right? Okay. So this one right here. We do calculations using this concept. So that's why I ask you to remember this. So I want to prove this case, which is this is what we want to prove using this concept right here. So this one, using this one, I want to prove this one. Okay, so now we know the little change of population or a little change of time is equal to change in rate into the initial population. How did I come up with this? Well, we initially, in the starting of this lecture, we said this one is equal to P. And to change it to equal sign, we just introduce something called R, which is the rate of change, and then the initial value. So this is the growth. So this is what it's equal to. To solve this, we're using calculus. So here it is how the calculus used for this. So you don't have to learn calculus if you are no idea what it is, right? Don't worry about it. Calculus is some method that Newton introduced in order to calculate these kind of things, okay? So keep that in mind. So what you do is usually first you multiply both sides by dt in this case. Okay. So when you do that, dt to dt cancel out, so dt will remain here. So you'll get something look like dt is equal to 0.10 dt be here, right? Now there are some dp's, dt's. Get rid of that. How do I get rid of this? Is where the calculus comes in. So this is a small values, right? Like for our graph that we introduced earlier, we divide these to smaller intervals, smallest interval that we can pick, and that is a dt or a delta t space. That's a smaller one, and then we'll calculate the change. And when you add all together, it will give you the total distance, as you remember, right? So like that, so we get the total value of population or total value of time using this symbol. I think you remember this symbol is nothing but you do the addition of all the things, all these intervals. That's what it means. So from here to here is the calculus part. From here to here is the calculus part. If you don't know calculus, don't worry about this one. Just remember this. So this is from here to here. When you do the anti-integral, this is what you get, which is ln of the positive value of p is equal to 0.10 t plus the constant. Okay. So this is what you get, right? This is a constant value, just some value. And using the property that I just introduced a minute ago, which is this one, if I have ln value, if I power it, it will give me the same value. So that means if I power it by e, I get p, right? So the property of this right here, so I'm using that in order to get rid of ln. That's what I do. So I know e to the power ln x is equal to x. I just want to get p out of here. So in that case, I will power this, and that will be equal to power of this. Okay. So just get the e to the power of this, and it will be the same here. So e to the power of ln x give you x means I get p on this side, right? I get p on this side. So and then I get e to the power 0.10 t, right? And since this is plus c, right? This is like something like 2 to the power 4. Also, I can write e to the power 2 plus 2, right? I can like this, or I can write this again, 2 to the power 2 multiplied by 2 to the power 2. These all are the same, right? I'm using this concept here, okay? So when I use this concept, this one I can write again, e to the power 0.10 t multiplied by e to the power c. So what is the e to the power c? That means a constant value to the power constant. So what does this means? Anybody who has done math or anyone? E to the power c, what you can call about this? This is also what?
A constant.
It's a constant, right? It's a constant because this is like 2 to the power 3. This is 8. It's never going to change. It's always 8, right? Like that, this is a constant. So I call it a, it's a constant, okay? It's never going to change this value, all right? So if I just call it a, I can say this is equal to a multiplied by e to the power 0.110 t, right? This is what I came up with. So this is the equation actually. So this is how you get the equation. So first you do this from here to here, magic step, remember, and take the e to the power of all like this. So that is just to simply take the e to the power of all. And I just call this constant value a. So this is what I get at the end, right? So this is the equation I get. Right, so now I have something unknown, which is a. I don't know what is a, right? what you know is the initial population. At the beginning, you know how much the population you have, right? At the beginning. At the beginning, what is the t value? What is t at the beginning? Time. What is the value of time at the beginning?
0.
Zero.
Isn't it just 0?
Just 0, yes. So just 0. So at the beginning, we know the population is 100 and the t is 0, right? That we know. So if I apply that to this equation right here, what I get is P equals, so the P initial value is 100, so I know that. So instead of P, I can write 100, right? Is equal to A multiplied by e to the power, whatever the value multiplied by T is what? Any value multiplied by T in here? If the T is 0, everything is 0, right? Yeah. So it is a T to the 0 power, right? Right. E to the power 0 is what?
1.
1. Why? Anything to the power 0 is 1. X to the power 0 is 1, right? Y to the power 0 is 1. Always, any number to the power 0 is 1. So in that case, this y will be 1, right? So that means A is equal to what? 100. You see that? Yeah? A is 100. So A is a constant, and in this case, the constant value is 100. So you get A is 100, e to the power, so since A is 100, I can come up with general value here saying P is equal 100 times e to the power 0.10 t. So that's what I get. Right, if you did not understand this, well, I will have the video of this posting there. And also you can go through these steps. What you have to know on this is remember from here to here, and the rest is just a general math. If you don't understand that, it's just to take the e to the power of everything. This one right here. But you should be able to figure out this one right here. Okay. So keep that. So 3 steps. 4 steps. 1, 2, 3, and 4. I like you to remember this. Okay. And in general, you can write this equation because of that is equivalent to this at the end. So that means what? If you have a dp by dt equal rp, always have it look like this and this equation. Okay. All right. So use that. Okay. So this is a dp by dt is equal to this equation right here. Okay. Right, so that is that we're going to use this equation on the next lecture. That's why I'm just pointing out on and on. Are there any questions? Are there anything that you don't understand on this that I should go over? Is there any piece of this that you don't get it at all? Even I just talk about something like rocket science. No, everybody got it right? Yeah. Okay then. Sounds good. So so this is, if you're using this equation, so what is the benefit of why we're doing this? Well, you can see now we came up with the bacteria 100 in a container, and we measure on each hour, right? Each hour we measure this, and we see that there's R rate, which is 0.10. And after some hours, we calculate and see how much the total population we have. That's what we calculated. After some hours, how much population we have. Okay, so this is what we did. And then we came up with some value. So you notice this in this equation, it's pretty easy to calculate that, right? So then the total population, that's what we're looking for, will be equal to initial population, which is 100, multiply by e to the power. So e to the power thing is you can calculate by your calculator, and this is the rate of change multiply by any given time. Like for example, 10 hours. If I want to calculate it straight ahead, I can calculate that. For 15 hours, I can just plug this up and then calculate it for that. So this equation will give you any number of time, how much is the population going to be. So it's very easy in that case, right? Yeah. So instead of we have these kind of calculations and then we don't know how to solve, now we have a very simple, straightforward way to calculate it, right? So that's what the whole idea of this. That's why I'm just showing you this. Uh, this is called the analytic solution, analytical solution to this. So analytical solution of this is nothing but calculating like that. So I'm not asking you to do the analytical solutions, all the equations that we have here, because why? Because you don't know how to do the calculus. If you don't know how to calculus, you don't know how to bring from this step to this step, right? So since you don't know from this step to this step, there are no ways that you can do this. So, but if I have this kind of solution, yeah, so we can solve this. So this is why I just showed you this. But I'm not asking you to do this calculus stuff. But remember how you get that. Okay, so this is a one question I usually ask in exams for. That's why I ask you to remember that. But in case of this semester, I'm teaching everything online, and your exams are open book. So then there's nothing to remember, right? You just can look at it all the time. So, but like you to understand things here. So I will ask, test your understanding on this. Okay, right. So then, what else we know? We know the growth rate, which is nothing but uh, the we calculate growth rate is dp by dt is proportional to initial population, right? So that's what we calculate, right? And then we said this is only for the births. So then you have a container, you have the birth of the people, right? Okay, so that means uh, nothing comes in from outside, nothing goes out from this container city or whatever, right? But we can apply the deaths here. So the death also causing a problem in order to the change the population in this container. So usually the death rate comes into play here, right? So then actually the birth rate, so the growth rate is actually a bit difference between a birth rate minus the death rate. So you have to consider this one too. Okay, so you have to consider that. So that is what we're going to look at in the next lecture. One after the next lecture. So I will try to finish this soon. And then we're going to talk about births and deaths as well. Okay, all right. So we did not apply deaths up to now. We just have talk about only the births. So how are we going to play around with deaths? That's something else that we have to discuss. Okay, so this is that all for this lecture. So if you have questions on this, please ask, because I cannot read your minds again, all right? So only way that I can do something is if you ask, I can answer, right? So make sure you cooperate well and make sure you understand things, okay? If not, please ask, okay? Right, so let me move to the next lecture here, which is how to, what we're gonna do with the equations we learn. What is the usefulness of it? So here it is, a very important one. So this one we're going to talk about radioactive substance. I was addressing this at the beginning of the class as well. The beginning of the semester. Few times I was talking about this. What is this? The radioactive substance means when it's a carbon 14 that we can calculate the age of the bonds and stuff like that. We were talking about that since the beginning of the semester. What is the use of these things, right? So here it is. So in this one it says the constant of a proportionality, constant proportionality of a radioactive carbon, approximately this much, right? So that is, what does this means? Well, this means the decay rate of this per year. So that means how much is decay per year as a percentage. You can give it like this, right? How did I get these extra zeros here? Well, what is this means is, again, if I say a percentage, usually you do is 0.01200968 divided by 100. This is what percentage means, right? Okay, so right, so this is eventually is equal to 0.00001200968. Okay, so this is what it's this is equal to. Okay, so then it says, well, the proportionality constant is this much. So this is what the value is. This is the rate of changing, right? So this is the rate of changing. So if you get the proportional equation, what is this says is after some time, changing a quantity of your the amount of carbon in your bone, the change of that is equal to actually proportional to the initial quantity. And to change this proportionality, we just introduce a constant R, right? Just like the population growth that we were talking about. And this value is given you as this much. So this is the same thing that you did in the population growth. So there's no much different here. So now I can say, well, it is a negative value. Why is a negative? Well, because this is a decaying. This is not adding anything. In a population, remember that we add the population growth, right? The population grows little by little. So it is going up, the value. In here, it's decaying. That means after bone, after the human or whatever it is dead, this one is decaying rate. So that means it's going down, the value. So that's why it's a negative, right? And then 0.0012, this is the rate of change things, okay? 68. And then the Q is the initial value, right? Okay, so this is the equation for change in values when it comes to carbon 14. And we know how to solve this now. So what is the equation for that is any quantity will be equal to initial quantity multiplied by e to the power RT. In this case, the initial quantity is Q0. I don't know that. We have to know that to calculate the age of the bone. And so you multiply that by e to the power. The R is this value, which is this value right here, and then the T. So if I know the initial value, I can calculate this for any T, right? So that is the good part. So that I can calculate this for any T, right? So then I know how much it will be in a 10 years time, how much it should be in 20 years time. So I can calculate like that. So let's do a real problem here. So I hope you understand up to here. If you're not, please ask again. I cannot read your mind, okay? So here it is. Suppose the proportion of the carbon-14 mummy is about 20% of the living human. So this is a human because we're talking about mummy, right? So the mummy is nothing but human that stored in a tomb for a long, long time. And you go and look at it, and then you take the bones of it and then test it. And then see, oh, okay, it has a 20% of the carbon of a living person, right? So living person means, let's say, well, I have carbon of 500, let's say, for example. And what is 20% of this means? 20% of this means if it's a living one, I have this much, it says, right? So if this is 1, so that means, well, how can I say this? Well, yeah, so let's say if it is, if it is 100, then if the starting value is 100, then that means 20 in there, right? And I can say if the starting is 1, it's just 20 divided by 100, right? If the starting is 500, then 20 divided by 100 multiplied by 500. So that's why this percentage is important. Okay, 20 over 100 is important because of this reason. Right, so this is what it means. So whatever the initial value, multiply by this. Right, so that's what actually having here. Right, so this is equal to the rate of this. So this is also, it says, I know this value, which is this one is already given to you. And this quantity is also equal to what we know is initial value to e to the power this whole thing here, right, into t. So this is a one way of calculating this q, right? And also it's given me in this way, which is, it is, if it is 100 is 20, whatever the q value right now is equal to 20 over 100 multiplied by q, right? So it is this. So that means what? I know this value in these terms. So there are two ways to calculate this. Did you understand what I'm talking here? Again, let me repeat this, right? Let's say you have a quantity of, you're supposed to have Q, right? This is what you're supposed to have, but it says now I have 20%, right? Okay, this is what it says. The 20% of the living human. So that means you have only 20% from the living human right now. So that means some amount, 80% decayed, right? And I want to calculate the time it took to decay 20% or the 80%, okay? So how do I calculate this is, this means if I had 100 at the beginning, now I have 20. So that means if I have 1, it has 20 over 100. How did I get that? Well, you divide 100 both sides. So this one will be turned to 1. This will be this. Then I'm asking, okay, then what if I have Q, right? So that means you have to multiply this by Q. So then you have to multiply this by Q. This means this much I have, right? So this is also equivalent to nothing but, so this is the initial Q, right? Right. So this is also equal to, from our equations, we know this is equal to this, right? E to the power 0. Whatever the value, right? So this is what I came up with. So in this case, I get Q to Q cancel out, initial value to initial value cancel out. So this means I get 0.20 is equivalent to e to the power this value on 20968 t, right? Again, the same property. Remember that we had this property of e to the power something here, right? Remember what we had? So if we have some values here, right? And then the t. And how do I get the t down? What did I do?
Take the natural log.
Take the natural log of both sides. So if I take the natural log of both sides, this side, I get ln 0.20 and equivalent to ln of e to the power whatever the value t, right? This is nothing but minus 0.00012 whatever the value t, right? Right, so that's what here, okay? So So that's what this equation right here. So that means on this side, I get ln value of 0.020, right? Equivalent to minus 0.0001200968 t. So how can I find t? Well, you divide both sides by this value. So if I divide both sides by this value right here, I get t in one side, and the other side I have ln 0.20 divided by negative 0.00, oops, 0.120968. You know how to calculate this. If you have a calculator, please let me know what is this value. If not, that's fine. Does anybody have a calculator? Want to calculate this? ln 0.20 divided by this value. What do you get? Should get 13,000 years. Something approximately 13,000. That's what you should get. 304 years. Right? So this is simply, we calculate the age of a mummy like this, right? So that is useful. So that's why I teach you this. Some people there are, if you are majoring something like this, who's more nature, whatever the archaeology or whatever you call the subject, I'm not sure. But so if you are in that subject, if you really want to calculate the age of this, yeah, well, if you are not math major or not, you may have to know these equations, right? Or you're supposed to have an equation, you're supposed to have a software that calculate it for you, right? So either way, it's not for the math people only. So for the other people who are really interested in ancient things, may have to calculate things like that to calculate the age, right? So I just showed you how you calculate the age. So this is maybe up to now, most people didn't know that. They were thinking the magic would do that. Oh, it is not the magic, it's just simple calculations will give you the age of those things. Only thing that you have to know is, I don't know how you decide that on dinosaur, but you have to know how much percent of that remains in a dinosaur bone. So maybe you have to get the much closer mammal. Like for example, if it is a mammoth or that is a group of elephants, so you may compare that with the elephant and calculate the age of a mammoth. But when you're thinking of some other animals like crocodiles or something like that, you have to come up with some closest species to estimate the value of carbon remains, right? Right. So that is something. So this is a part. This is the part you have to come up with for every species out there in order to calculate the age. If you don't know that, well, that is, you won't get the accurate date on time. Okay, so that means you have to get the similar species group in order to calculate that, right? Okay, keep that in mind as well. All right, so then let's move on to the next one. This is a practice exercise for you. It's a radium. Radium is another radioactive material. Its decay rate is this much, right, per year. Determine the the half-life. Oh, I did not introduce you the half-life. Half-life is the time period it takes to decay half of that. So that's what the half-life means, the half of that, right? Usually the half is what? 50%, right? Anything 50% is the half, right? Okay. So if you get, like, for example, if the good is $80, half is $40. So what is the discount? 50% discount, right? So that's how you calculate. If you want to calculate this, what this means is, well, if it is 100, you get $50, right? And if it is 1, you get 50 divided by 100. If it is $80, then what you do? divided by this, multiplied by 80. So this 0 to this 0 cancel out, this 0 to this 0 cancel out, ends up with $40. So that's a half. So like that, we consider half of this means 50% of the value. So we know that percentage now, 50%. So in this case, it's asking what is the half-life of this material, right? Right, so then that means 50% of this, right? So that part I know, right? Divided by 100, right? Okay, so that's the quantity remains. This will be equal to nothing but, so 50% of the original value is equal to original value multiplied by e to the power, so 0.0000427 t. Okay, let me ask you this question. Why is it negative?
Because it's decay.
It's decaying. Because of decaying, we put negative value, okay? If it is growing, we don't put the negative value, right? Remember that. So this one to this one cancel out. So this is a half-life I'm calculating. So this side will be 0.50. And on the other side, we will have e to the power, right? Negative 0.000427869 t. Now, what is the next step? I want to bring this t down, right?
Take the natural log of both sides.
Take the natural log of both sides. So it's the natural log 0.50, and then this will come down automatically, then it will remain like this. Okay. The reason you get this like that is we know ln e to the power x is equal to x. This is a rule, right? This is why I can take this out. That's why I take natural log of both sides. Okay, right. So when you get that, so that means the t, to get the t out of this, so I divide both sides by the same value. It's the same value. So that means that t is equal to nothing but this value right here. So that gives you the half-life of radium 226 will give you by 1620 years it takes in order to decay half of the radium. So if you have full radium on something, to decay half of that, it takes 1620 years. That's what it means, okay? Right, so keep asterisk on this. Keep asterisk on the previous one, which is this one right here. So make sure you learn this. Make sure you learn this. Why? Well, that is very hard for your head if you never used this before, and if you didn't do this depth of calculations in mathematics before. There's so many things going on. Your monkey mind runs around. You are just on other websites while I'm talking and things like that. So all that happening on your end. So there's a pretty good chance you're missing this. So that's why I want you to repeat in your brain the same thing on and on until you're comfortable with it. So keep asterisk on those two slides and study those two slides, and that is important, okay? So this is the usage of the equation that we were talking about in system dynamics, right? We look at the analytical solution, we came up with this equation. Now this is a practical use of it. Right, so this part, the report for the dynamic models, I will talk about this because I'm going to give you the project proposal very soon. So I will put this on a side for a minute, and then I want to talk about the next chapter, which is on the Friday quiz that covers. So for the next 7 minutes, I will start that, and then I'll come to this if I finish it soon, okay? So yeah, so make sure you understand these two and the half-life. Those are three things I want you to point out here. And I'll come back to this lesson right here anyway when I'm introducing how to write the proposal, okay? Right. So let me go to constraint decay. So I have to finish this by Wednesday because you have a Friday quiz. Right. Okay. So now here we come up to some level of maths now, right? So we can calculate things. First, I introduce you calculus. Then I introduce you rate of change. Then I showed you how the population grows and how you're going to put that in a Vensim. If you did the tutorial, now you're comfortable with that. And then I showed you what is the analytical solution, how you're going to solve that analytically. And we end up with this equation, right? So far, so good. We can calculate things. Right. So then the finite difference equation we talk about. What is finite difference equation? Anyone? If you recall what I said, that is the big name, finite difference equation. What it means is what?
It's like the initial population is equal to the old plus the change.
Yes, exactly. That's what it is, right? Initial population is equal to, I mean, the new population is equal to initial or the old population plus the change, right? So that is what we talk about one of those chapters. And well, that is this equation right here, the same thing, all right? Okay, so this means the new one, which is a PT, is the new one, is equal to, if I take this one this way, it will be plus delta P plus P previous value, delta T minus T. So that's the previous value plus the change is equal to new, right? That's what we got here. And so, well, from here, we come up with this equation, right? And this equation, what it says here is this is equivalent to nothing but rate multiplied by, so the change of this is equal to nothing but the rate multiplied by the previous population. Previous population is this, right? And multiplied by delta t. How did I come up with this equation? What does this means, right? So that's the next question. So this is what we came up with. The initial equation is dt is proportional to initial population, and we said dp is equal to dp by dt is equal to rp, right? So this means what? dp means a change of population over change of time is equal to initial rate of the previous population, which is nothing but t minus delta p. This is the previous time, right? So that means the previous initial population. We know this, and so the delta change is equal to, you multiply both sides by delta t. This is delta t. This cancels out. This is nothing but r p t minus delta t multiplied by delta t. So this is what, this part I just talk on and on. So this is what this means. So it is not like you derive this from this. No, that is not the case. So I just showing you two ways to show the same thing, right? This all two equations. This one, these two. So this is how you just show that. This is how you show by the difference equation, right? Yeah, even is showing it like this is a big thing actually showing there. Okay, right? Is that clear? Right? So this one we talk about on and on up to now, so many lectures. This one also I introduced in one of the lectures, right? So it shares both showing the same thing. Right, so that is the initial thing. And let me talk about carrying capacity and stop today, and then continue on Wednesday. The carrying capacity is pretty interesting thing. What does this means is, so next 2 minutes I would like to talk about this, is let's say that you have area population of deer population, right? And this is a park, let's say. Unfortunately, now it's burned. So I'm really, really sad about the animals over there. Well, I cannot say all. So nobody can. They're caught in fire, actually. The babies, nest, birds, all these rodents and things like that. Well, anyway, so when you're talking about the container like this, they have a habitat, they have food. What happens when they grow and they're growing too fast, and then these resources is not enough for them? Then what's going to happen? Well, then the population is getting larger. They don't have enough food. They will expand their territory, right? So what does that means? Well, expanding the territory means they're going out of the bounds, and then they're going to invade little by little to the other territory. So this happens in anything, not only animals, it can be human as well. So, all right. So like that, it's carry on beyond the area. So that is what the problem. So in order to nail this problem, you're always calculating what is the carrying capacity, what is the amount that you can support in this area, how many deers can support the resources I have. What if it is go exceed on that? So this issue happens. So that means you have to control either population or something. So to measure this, this is what carrying capacity means. So we'll talk about this next time.